So, to recap, we started with a 3D model representing planet Earth as a unit sphere with adjustable constants for time of year, the Earth's axis tilt, and the latitude of a point, and then wrote a parametric curve which describes in terms of t, which is an angle representing the time of day, so goes from 0 to 2 pi, representing a full turn of the Earth during the day. And what this parametric curve represents is the path of a point on the surface of the Earth around the Earth during that day. We then took just the x component of that parametric and turned that into a function of one variable. We renamed the time of day variable to x so that it would show up as the x coordinate on the graph. And the value of this, recall, is how far front to back toward the sun you are. So a positive value means that you're somewhere on the Earth on the lit side, and a negative value means that you're somewhere on the Earth on the dark side. And when the value of this function crosses over from negative to positive, that's sunrise, and when it crosses over from positive to negative, that's sunset. So this is a very interesting function. We want to know about what this function does when it equals 0. Before I get started with that, I'm going to do some algebra using Desmos as a tool. As far as this function's concerned, x is the only variable. The other letters that you see are adjustable constants. They're adjustable with these sliders here. So I want to do some algebra where I take expressions like this, cosine little s, cosine a, cosine little l, and factor that out and replace it with capital A, and then write capital A equals that expression down here. And Desmos knows how to handle that. It knows to substitute this in here. And so we get the same graph. So I'm going to do that with that expression and with this expression, capital B, and this, capital C. And there we go. So this is the same function now. It's just shorter because I have moved the constants out into their own letters. We then want to look at the derivative of this. So let's just compute the derivative by hand. Now that I've got those constants in there, it's easier to see what the derivative of this is supposed to be. The derivative of cosine is negative sine, so the derivative of that first term is negative a sine of x. The derivative of sine is cosine, so the derivative of the second term is negative b cosine of x. And the derivative of a constant is 0. I'm going to color this yellow to be consistent with the previous video. So now we have the green curve, which again, that's measuring how far front to back we are on the Earth's surface toward the sun. So here's where it's high noon, I guess. And here's where that's sunrise. We want to know something about the derivative of the green when the green is 0. So I'm going to take the function here, that's the green function, and I'm just going to make a line that sets that equal to 0 and color it blue. Desmos knows how to graph that, which is kind of nice, and it graphs it as vertical lines. And even if I adjust the parameters, you can see that the vertical lines are always striking through the roots of the green function. That's what we're interested in. But we want to know the value of the derivative. That's the yellow curve at the coordinate of the blue vertical line. We want to know this point, right? And for that, I'm going to type something that looks like it came out of nowhere. I'm going to type y squared equals a squared plus b squared minus c squared. I derived that separately on paper. I recommend trying to do that yourself. Here's how you do it. You take this function and set it equal to 0. You take this function, the derivative, and set that equal to an unknown. Call it y. And then you try to solve that system of equations. You try to solve that system of equations for y squared. And when you do that, you can use trig identities to make all of the trig disappear. Try it. It's very fun. It's fun algebra. Anyway, this is what you end up with. You end up with y squared equals a squared plus b squared minus c squared. And you can see as I adjust parameters, let's color that a different color. Purple. Okay, so the purple horizontal line intersects the blue vertical line on the orange curve. Yellow, orange, whatever color that is, on the yellow curve. And that's even if I adjust parameters. Now, there's a throwaway answer down here where those two intersect, but I don't mind about that because everywhere where the green curve is 0, if I look for the intersection of blue with purple, there is an intersection with yellow. So the throwaway answer that's not a problem. That's not going to give us bad information because all we really care about is how fast is the green function changing when the green function is 0. And this equation is going to tell us that. And you'll notice about this equation that there are no x's in it. So over here, I have made a new graph with the same a, b, and c, except that I've replaced s with x. So I've renamed the time of year to be x. So time of year is now on the horizontal axis. I have the same a, b, and c as before. I have the same Earth's axis tilt and latitude as before. And I have done a little bit more algebra. You can see where this came from. You've got a squared plus b squared minus c squared. That came from here. I did a little bit more algebra to get, instead of the derivative, which tells you the speed with which you're passing through the twilight zone, I found the duration by solving for y and then dividing by that. And just to make it in minutes, I multiplied by what we computed as the duration of the sunrise or sunset on the equator in minutes. So that's this number. And so y should be the sunrise, sunset duration as a function of time of year. So what does that look like? Well, in the winter, that's here, that's on the ends here. It gets as high as almost 3¼ minutes. In the spring and the fall, it gets about 2 3/4 minutes. And in the summer, it goes up to 3¼ again. Plausible, right? What if we make the parameters really extreme? What if we move the latitude up like way closer to the equator? And then, or sorry, closer to the pole, I mean. So if you go closer to the pole, maybe not that close. Okay, there. So then you can see that this is not, it's not a sine wave. It's not a sinusoidal. This is pointier at the top than it is at the bottom. It kind of swoops on the bottom and comes to a narrow point at the top. So it's not quite a sine wave. Time well spent.